This is the ESP-DIVE, a submarine you can actually build to explore the underwater world in first-person view. Watch live video through its bubble cam, adjust buoyancy to dive or surface like a real sub, and conveniently steer it from your phone. I'm Max, and in this tutorial I'll give you the files, code, waterproofing tricks, and the steps so you can build your own working RC submarine and take it exploring wherever you dare to dive. And before I show you exactly how to build your own, let me take you through the prototyping process that got me to this point. It first started with an idea, suggested by many of you guys in the comments. Overwhelmed with this being the most highly requested project, I took on the challenge and got to work with a rough plan. I started by testing every single mechanism I desired to have in this sub individually, such as this DIY piston ballast for the submarine's diving and surfacing ability, comprised of a 5ml syringe, a rack and worm gear for linear actuation I had designed and printed, and an N20 micro-geared motor for driving the piston in or out. For precise actuation and controlled stopping points combined with a linear potentiometer, I figured a servo motor's control board would help do the trick. I wired a quick prototype of the submarine's control system using an ESP camera to stream live video and act as the brain, driving 2 piston ballasts, one at each end, balancing out changes in fluids, a high-power brushed motor for driving the thing forward or backward, and a servo for rudder steering. As a bonus, I also added a latching power switch and even a convenient wireless charger. To come up with the propulsion mechanism, I designed a magnetic drive coupling to keep the hull isolated while still driving the propeller in the water. A bearing holds the motor shaft in place in this special mount, preventing it from being pulled outward by magnetic forces and creating unwanted friction when driving the propeller on the other side. Getting the spacing between the couplings right was tricky. The closer they are, the less slippage, but neither could touch the container's wall in order for propulsion to happen. For the steering mechanism, I used magnetic couplings to convert one axis of rotation into another, turning the rudder left and right. To seal the acrylic pipe hull, I designed 2 end caps, one plain and one with a clear dome, each fitted with a rubber O-ring to keep water out. Next, I had to tackle the underwater reception problem, which had failed when I submerged my previous project, the ESP32 spherical robot. Since Wi-Fi cannot transmit underwater, I ran a coaxial cable from the controller inside the hull to an antenna supported by a piece of styrofoam at the water surface. For a proper test, I anchored the sealed tube with the submarine's prototype circuit to the bottom of my large jacuzzi and confirmed that the video feed along with the control of the piston ballast and headlight worked perfectly. After half an hour of it sitting at the bottom, I was fortunate yet again to have not a drop enter the tube. For the buoyancy test with some weights shoved inside, my objective was to roughly figure out what amount of weight would make the tube neutrally buoyant. After finding the right weight, excluding the surrounding plastic that adds buoyancy, I compared it to the weight of the electronics with the tube to estimate how much ballast I'd need for neutral buoyancy. With the weight and balance figured out, I needed a clean, reliable way to wire everything up, so I designed a custom PCB to keep the control circuit compact and organized. I started by designing the schematic, essentially the wiring diagram, using my prototype circuit in front of me for reference. The first step was to gather and place every component onto the canvas: the ESP32 camera, transistors, LEDs, connectors, and more. Then I used the built-in AI assistant to generate a schematic layout plan I could follow based on what it detected. For power control, I adapted Dave Jones's latching power switch from EV-Blog, modifying it so the sub can be switched on and off with just the brief presence of a magnet. Next, I mapped quick connector pads for all the external components. For propulsion, I added a bidirectional motor driver for the main prop, along with connectors branching out to the 2 piston ballast actuators and the rudder servo for steering. I also included a resistor divider for battery voltage monitoring and a simple LED driver circuit for the submarine's headlights, which not only illuminate dark waters but also serve as a low battery warning. With the schematic complete, I moved on to the the PCB, I first shaped the board to fit snugly inside the cylindrical hull, then arranged the components according to how I wanted them to sit. Space quickly became tight, so I packed the layout closer and closer, using every millimeter I had available. For silkscreen, I managed to label every part and even fit in the project's name. When routing traces, I calculated thicknesses for both power and signal lines. Once the design was complete, I ran it through the AI design review tool for reassurance. The review confirmed there were no actual errors. That meant I could confidently export the design. And now you can download the Gerber for free to order the PCB. And if you're ready to start designing your own PCBs, check out Flux. With built-in AI tools, it makes designing boards like these a whole lot faster and smarter. See for yourself whether it lives up to the hype. Click the link in the description and give it a try. Then I jumped back into Autodesk Fusion to 3D design the same controller board and all the other components which drive the submarine according to measurements I took. This allowed me to model around them, positioned with the space constraints, forming the body parts which make up the whole submarine, such as the piston ballasts, end caps, couplings, motor mounts, different gears, the tail cone housing the rudder and propeller, front cap with the observation bubble, holders for ballast weights, and the frame which holds all the components within the ESP-DIVE. I spent over a month prototyping and perfecting this submarine design so you don't have to. And to thank you early builders, the STL files are 20% off for the first month only. Use code ESP-DIVE20 at checkout. Watching after the launch month, there may still be a smaller discount waiting for you. Check the link for the design files in the description. Once you have the files, feel free to modify them and drop them into your slicer, or leave them unchanged and just use the ready G-code files. Find all printing settings on the 3D model page. For filament, which you'll find linked below, I'm using Army Green PLA for the submarine structural parts and matte black PLA for most mechanical parts. Let's heat things up and print out the first batch of parts which make up most of the submarine. Thanks to my printer's massive build volume, it can handle every part of the sub in one go. For the best adhesion, turn on brim mode. It gives each part a stronger grip on the build plate, preventing tall prints from popping off, and enable supports as they also give you much cleaner surfaces on steep overhangs. With cooling on and peak speeds hitting 500 millimeters per second, a batch like this would take around 8 hours to print. To print the mechanical parts, enable much steeper support overhang angles, as parts like the propeller do not need supports. I slowed the print speed to maximize layer adhesion, as these parts need strength, and since they're small, there's no rush. Now that they're all printed out, we'll deburr the brims and remove the supports, revealing clean and ready submarine parts. The Elegoo Neptune 4 Plus nailed every print from the rear hull section to the delicate propeller. If you want to start printing your own projects or step up to a better printer, I've linked the exact machine I used below so you can get the same results. For the rest of the submarine's parts, you'll need things like batteries, a wireless charger, brushed motors with a driver, servo motors, the ESP camera with its SD card, potentiometers, connectors, through-hole and surface mount components, a PCB, wires, a 5-meter coaxial cable with antenna, rods, straws, screws, inserts, bearings, magnets, and weights. You'll also need O-rings, tubing, a clear ornament shell, syringes, and an acrylic pipe for the hull. Altogether, you're looking at roughly $125 US in parts, not including spares or shipping. Let's start with the submarine's dive controller board, the one that ties all the electronics together. Here's how to order it. First, get a quick quote from your PCB manufacturer by uploading the free Gerber file I've linked in the description. Just make sure a few key settings are correct. Keep it at 4 layers, super important for this design. Choose how many PCBs you want, set the board thickness to 1.6 millimeters, pick your favorite color, and select Remove Mark to keep the board clean from printed order numbers. Then simply add it to your cart and check out. The whole process takes just a few minutes. For my batch of 5 PCBs, given the color and complexity, the cost was just $6.80, and JLC PCB had them fabricated in only 3 days, excluding shipping. In the default green, you can get this board for as low as $2, and similar simple designs can be produced in as little as 24 hours. That's why I recommend recommend JLC PCB. They make getting high quality PCBs easy, affordable, and reliable. Click the link in the description, sign up to get $70 in new user coupons, and get your own ESP-DIVE controller board made. Let's start assembling the board by adding solder paste to the pads we'll be using. Then we can place the top side components, the 51 and 47 kilo ohm resistors for voltage monitoring, the 10 kilo ohm pull down resistor, and the N-channel MOSFET that drives the headlights. Once everything's in place, we'll solder each pin by heating up the solder paste with a fine tip iron. Or if you have one, we can use a hot plate to reflow them all at once. For the rest of the components, let's flip the board over and add more solder paste. We'll place the latching switch circuit parts, the P-channel MOSFET, 2 NPN transistors, and the 10K, 100K, and 1 million ohm resistors, along with the LED current limiting resistors. Once they're in position, we'll solder them into place using tweezers for precision. And that is it for the SMD components. Next, let's install the through-hole components. We'll start with the ESP camera's foundation by soldering two 7-pin female header rows on the top side. On the underside, we'll insert the 6 and 4-pin male headers for the motor driver and the servo headers. With the pins supported by a piece of paper, we can carefully flip the board over and solder those bottom side pins from the top. After that, we'll push in the JST battery connector and the 47 microfarad capacitor, solder them, and trim any excess pins. Back on the underside, we can install and solder the DRV8833 dual channel motor driver, making sure to keep its orientation correct. With the motor driver installed, it's time to bring in the brain of the sub. This little ESP camera board does it all: Wi-Fi control, live video streaming, onboard SD recording, and even battery management, all in a thumb-sized package. The Xiao ESP32 S3 Sense. Let's unpack the Xiao and separate the camera expansion board from the microcontroller so we can solder on the pin headers using a perf board for stability. Then we'll wire the battery connection from the bottom so it shares power with the DIVE controller PCB. The extended pin header mount keeps the whole board seated as far forward as possible inside the bubble for a clear view out front. Next, let's trim the protruding pins so the board sits flush against the 3D printed front cap and install the 12 headlight LEDs controlled through the camera dev board, taking a little extra care to get them standing perfectly straight through the front face. Finally, we can clip on the Wi-Fi antenna, snap the camera board back into place, and just like that, the brain of the sub is ready. Thanks to the fast S3 chip, the control and video feed feel near instant with minimal latency, which is really important underwater. And with its 3 megapixel wide-angle camera, you get a clear, immersive view ahead. To get your Seat Studio Xiao ESP32 S3 Sense camera board, check the link in the description. To program the board, let's bring it to the computer, plug it in, and open this camera web server application code by S60SC on GitHub. I've linked it for you in the video description. In the repo, download the zip file, unzip it, and rename the folder by removing -master from its name so that all the files open correctly with the main .ino sketch. When you open it, the code should look like this. Before we upload, let's make a few changes to match our setup. In appglobals.h, comment out any ESP boards we're not using, then uncomment the Xiao ESP32 S3 line to enable it. Scroll down a bit further and set peripherals and the board's PWM functionality to true. This turns on things like the motors and other connected devices. For a feature like the blinking headlight low battery warning, I had to code it myself. To add this, let's head to the peripherals.cpp tab and replace this function with a slightly longer one. Don't worry, I've included this snippet of code in a text file you can grab with the project files so you can simply copy and paste it. Here's how it works. When the battery voltage drops below a set threshold, the code detects it and drives the headlights to blink in a repeating pattern. Once we've made these changes, we just need to prepare the board. Go to Tools, select the Xiao as the board, enable CDC on boot, choose the correct partition scheme, enable PSRAM, and pick the COM port your board is connected to, then click Upload. When the upload finishes, grab a micro SD card with at least 4 GB capacity, plug it into your computer, and copy the included data folder to it. This will store your Wi-Fi credentials, keep your settings saved, and record video footage. Eject the card, insert it into the shell, connect a 1S LiPo battery, and short the 2 reed switch pads at the back to power the system up. Now let's set up the app. Pull out your device, go to Wi-Fi settings, and connect to the ESP camera's access point network. Then open a browser and type in this universal access point IP. When the control panel loads, tap Start Stream to see the live video feed. If it's upside down, go to Picture Settings and turn on V-Flip to correct it. There we go. At the top, open Edit Config, Peripherals, and enable remote control and servo use. Scroll to the voltage monitoring section, set the low voltage warning to 3.5, assign the monitoring GPIO pin to 6, and enable voltage check. Next, go to RC config and set the headlight GPIO to 43, the forward motor driver pin to 1, the reverse driver pin to 2, and the steering servo pin to 3. Under the servo tab, which usually controls a camera, we'll repurpose it for the piston ballasts. Set pan, the front piston, to pin 4, and the tilt, rear piston, to pin 5. Once everything is set, scroll back up, tap save and reboot, and the board will restart with all your new settings applied. Once the camera restarts, we'll reconnect to it, refresh the web server, and boom! We now see info like the live battery voltage. When it drops below 3.5 volts, the headlights will automatically start blinking as a low battery warning. Turning on the stream will also reveal a controller icon. Tapping it brings up sliders for driving the submarine and a button to control the headlights manually. In the camera control panel, we can adjust peripherals like the piston ballasts and set the stream resolution. Keep in mind, higher resolution means lower frame rate, and lower resolution means a much smoother stream. For the best of both worlds, I recommend SVGA 800 by 600 pixels. It runs at around 20 FPS while still giving a nice clear image. Finally, if you want to watch your recordings, head to the Playback and File Transfers tab to view or download videos saved either manually or by motion-triggered recording. Now let's assemble the piston ballasts that make the sub dive and surface, starting with the rear one. First, we'll melt in a pair of 3mm M3 threaded inserts. These will join the rear mounts to the front frame later. Next, take a 5mm syringe and modify the plunger. Cut away the supporting plastic wall so the rack gear sits flat. Then trim off one of the flange tabs, leaving the other rounded. We'll drill a hole in the remaining tab for the M3 bolt, slide the syringe into its mount, trim any extra flange that interferes with movement, and secure it with the bolt. Once that's done, the front frame piece should snap neatly into place. Next, let's install the linear slide potentiometer that tracks the plunger's position. We'll start by straightening its 4 pins, then insert it and secure it using any pin that protrudes through the board. Now we can slide the rack gear onto the potentiometer slider and glue it to the flat section of the plunger. For the drive system, we'll mount an N20 micro metal gear motor into its cavity, snug up against the syringe, and secure it with a pair of M1.6 screws. Add a drop of superglue to the motor shaft and slide on the worm gear. This is what moves the rack gear in and out. We'll also install the control board, which comes from a 9-gram servo. Just desolder it from the motor and rotary potentiometer, trim a bit off the motor side if it doesn't quite fit, then seat it in place and secure it with a dab of superglue. Next, let's set up the trimmer potentiometers that define the upper and lower limits of the plunger travel. Take 2 rotary trimmers and bend their legs so that 2 of them connect in the middle, leaving only a front leg pointing up and a separate back leg pointing out. Solder the join pins together at the back, then push both trimmers into their mounts. Bend and trim the pins so they sit neatly. Now solder the left trimmer's front pin to the first of the linear potentiometer's 4 pins and tin the rest. Solder a wire from the right trimmer's front pin to the top left pin of the linear potentiometer. Then connect the left trimmer's remaining pin to the ground potentiometer pad on the board and the other trimmer's remaining pin to the potentiometer power pad. Finally, connect the board's center potentiometer pad to the second pin on the linear potentiometer. From here, we'll hook up the motor. Using a couple of wires, connect the board's motor pads to the motor pins. Polarity might differ, so double check later that it moves in the correct direction. Finish by soldering on a 3-wire cable pinched from the disassembled servo for signal, VCC, and ground. Once everything is wired, we'll tidy up by gluing down any loose wires so they don't snag during operation. That completes one piston ballast. The second one assembles the same way, except its frame uses 3 threaded inserts in different locations. When both are done, they should look like this. With all the peripherals ready, let's connect them to the control board for a quick test. The wireless charger should make the charging LED blink, the drive motor should spin both directions, the steering servo should move without jitter, and the piston ballast should travel in and out. Each piston still needs to be tuned so the plungers stop precisely at the end of their travel. So let's jump right into tuning the first one. Start by setting the slider value to 180. This represents the maximum water ejection. Adjust the lower threshold trimmer while the piston moves down until it stops right at the end of its stroke without straining. Next, set the slider value to 0 and repeat the process for the upper threshold trimmer, adjusting it until the piston stops at the top end correctly. Test the piston by moving it back and forth a few times, trimming both trimmers little by little until it stops cleanly at all 3 points. Fully in, fully out, and halfway, with no grinding or motor strain. Once this one is dialed in, repeat the same process for the second piston ballast so both behave identically. Empty at 180, full at 0, and stopping halfway at 90. By running the pistons at different positions, you can also tilt the submarine slightly up or down in the water, which is handy for better underwater maneuvering. Let's transition to the final assembly by disconnecting the quick test circuit from the control board and focusing on the front frame, where the wireless charging receiver and power board will sit. First, we'll extend the coil's wires by pre-soldering these 2 wires onto the board with loose ends for now, then superglue the charging board into its cavity. The receiving coil can be glued into its socket in a slight curve. Bending it is completely safe. To make docking easier, we'll also secure a 5mm neodymium magnet here so the transmitting coil snaps into place when charging. Next, let's prepare the boost converter for the 5-volt peripherals. We'll desolder both USB connectors to make it more compact, then solder on short wires for the battery input and boosted 5-volt output. With that done, we can slot the module into its front mount, route the wires outward, and glue it securely. For power control, we'll be using a reed switch, a magnetically activated switch that lets us turn the sub on and off without breaking the watertight seal. Carefully bend the pins down to fit, taking care not to crack the glass housing, then slot it into the side cavity. Test it once inserted to make sure it still works. Finally, dab on some superglue, trim the pins, and solder extension wires so it's ready to connect to the control board. Now let's hook up the drive motor. We'll use a pair of JST connectors. Solder the female connector to the motor pads, giving it enough wire length to reach comfortably. Next, we'll handle power wiring. Solder the charger board's 2 wires to the power input pads, then connect the boost converter's 4 wires, 2 for the battery input and 2 for the stepped up 5 volts output for peripherals. For power, we'll be using a couple of high discharge 500 mAh 3.7 volt LiPo batteries. We'll wire them in parallel to double the capacity while keeping the system 1S friendly. To do that, solder 2 female JST connectors and 1 male JST connector together in parallel, creating a shared connection point for both batteries. Now we can slide both batteries into their slots, connect them using the parallel joint we just made, and plug the joint into the control board, carefully tucking it under the surrounding wires. After a bit of wire management, we'll glue the control board securely to the frame so it doesn't shift around. Before connecting the reed switch, I recommend unplugging the battery to prevent the board from powering on while we solder. Once the two reed switch wires are soldered, we can reconnect the battery and test the magnetic switch to make sure it works before sealing everything up. Shave down the reed switch pins if they protrude. Now let's route the antenna wire. Push the UFL to SMA adapter through the hole on the right side of the PCB and connect it to the show's antenna port, leaving the SMA end free for now. Next, let's plug in the servo, rear piston ballast, and front piston ballast in that order. Before mounting the front ballast, connect a 6mm PVC hose to the end of its barrel by twisting it onto the needle adapter. Mount the piston ballast, route the hose through the loops, and secure it with 6mm M3 screws. The front frame is almost done. We just need to reconnect the coil to its charging circuit using the pre-soldered wires and cover the joints with heat shrink tubing. Moving to the rear frame, install a threaded insert for the rear ballast mount, then secure the drive motor with two M1.6 screws. Then install the 9-gram rudder servo with its included screws. Give the rear ballast its shorter PVC hose and slide it into place, fastening it with a single 16mm bolt. With both frame halves ready, join them together and secure with a round-headed M3 screw on each side. If needed, grind down two cylinder-headed M3 screws to make them fit in the hull. Route the front ballast hose through to the rear so both hoses stick out. For wiring, extend the male JST connector, plug it into the female side, secure it with a dab of glue, and solder the leads to the drive motor, keeping in mind you might need to swap polarity later during testing. Tidy up the wires with a bit of maker magic so everything sits neatly. Finally, let's extend the antenna to the surface. Use a 5-meter roll of 2.5mm coaxial cable with SMA connectors. Route the female end through the rear, temporarily loosen the motor to make room, and slide on heat shrink tubing before connecting it to the adapter on the ESP camera. Use pliers for a solid connection, then shrink the tubing to seal it and prevent condensation. Secure the joint in place so it doesn't interfere with the front piston's movement. At the end of the coaxial cable, we'll secure a short 2.4 GHz antenna, and with that, the wiring on the sub is complete. Building a submarine can feel intimidating, especially the electronics, but you'll pick it up fast if you dive into electronics every day. Reading Elector magazine is how I stay sharp. Expert tips, real projects from makers worldwide, and ideas you can use right away no matter where you're at in your journey. Right now, you can join for half the regular price, but only for a limited time. Check the link below and get ahead on your next project. Now let's shift focus to the mechanical side. We'll start by assembling all 4 magnetic couplings. Press in the 5x3mm neodymium magnets, alternating their polarity, north, south, north, south. This way, when you bring another coupling close, the magnets will snap together but resist rotation, giving a strong, reliable drive. For the rudder, we'll use the same alternating polarity pattern but with only 3 magnets per coupling. This pair is unique. It converts rotary motion from one axis to another to steer the rudder. Any coupling exposed to water should have the magnet surface sealed with superglue to prevent corrosion. For the couplings inside the hull, just a few dabs of glue are enough to keep the magnets secure. We should now have 2 pairs of couplings, 1 pair for the rudder and 2 for driving the propeller. To keep the motor shaft from being pulled outward by magnetic forces and creating friction, we'll install a plastic ball bearing in this 3D printed mount. Push the drive coupling into the bearing, secure it with glue, then gently heat the motor shaft and press on the coupling assembly. When done correctly, it should spin freely. Next, grab the rear cap and melt in a couple of threaded inserts. Then slip on the 44mm rubber O-ring to seal the back. Insert another bearing. This one supports the propeller shaft using a plastic bearing with glass balls to prevent corrosion, even in salt water. For the propeller shaft itself, we'll use a 2.4mm spray can straw, which avoids rust. Secure it to the driven coupling through the bearing, roughen the mating surfaces, and use epoxy to lock everything in place so nothing shifts. To keep proper clearance while drying, slide a bent 1mm metal spacer under the coupling to hold it slightly away from the wall. While that cures, we can assemble the rudder. Using another piece of plastic straw for the steering rod, slide it into one half of the rudder and feed it through the top, marking and trimming about 20mm from the fin. Reinsert it, this time with the receiving magnetic coupling pressed in for a snug fit. This also sets the rudder's motion limits. We'll install the third and last plastic bearing at the very back of the tail cone to support the propeller shaft. Glue the rudder shaft bypass connector to the exposed end of the straw so the rudder can pivot freely without interfering with the drive shaft. Let's finish the rudder assembly by installing the bottom fin using the same length of tube as before. Now we can connect the rear cap with its propeller shaft to the tail cone. It should fit snugly. Secure the rear assembly to the frame with a pair of 16mm bolts and test that the output shaft spins freely. Before attaching the propeller, trim the output shaft so about 6mm of it protrudes. With the parts disassembled, this is the perfect time to route the antenna cable through both sections and out the rear of the tail cone. Seal the hole where the cable exits with superglue first, then reinforce it with hot glue. Be thorough here, since any leak at this point could flood the hull. Don't be afraid to add a little extra superglue until you're confident it's watertight. Once everything is sealed and cured, reassemble the rear pieces and slide the propeller onto the shaft. Secure it by heating a clipped piece of LED pin, aligning it with the propeller's holes, and quickly pushing it through. The best part is this pin can slide out later if you ever need to remove the propeller for maintenance. With the pin locked in place, there's no way this propeller is coming off. To keep the motor cool, we'll stick on the two heat sinks that came with the ESP camera. These fit perfectly on top of the motor and help dissipate heat during long runs. Now let's finish the rudder mechanism. First, fuse a short section of bicycle spoke into the rudder coupling and insert it into place, making sure it moves freely inside its cavity. Trim off any excess spoke, then install the servo drive gear and the driven rudder gear onto the shaft. Carefully slide the rear section over the coupling and fasten it into place. To set a limit on how far the coupling can sit from the wall, we'll use a short piece of pen tube as a spacer. With the rudder held straight, glue the driven gear to the shaft, and just like that, we have smooth, responsive steering. Let's install the piston ballast hoses into the rear cap. Trim each hose to length so it fits the sockets with a few millimeters of slack. Run a small bead of superglue around the edge and press them in with pliers. For extra security, add another thin layer of glue around the outside to minimize any chance of leaks. Next, we'll form the fixed ballast to make the submarine heavy enough to dive. We'll use 1/4 ounce iron wheel weights. Trim the edges and peel off the sticky backing before pressing them into the weight mounts. The frame holds 8 in the front and 8 in the back, arranged in rows of 4. For the front face, grab 1/2 of a 40mm clear ornament shell and trim off the tab so it's flush. Glue the shell into the front cap, making sure there are no gaps. Then follow up with a little more glue from the inside for extra sealing. Slip on the O-ring to finish off the seal. Before final assembly, it's crucial to do a seal test. Submerge the cap underwater and check for leaks. Even if you don't see any bubbles, that doesn't mean there aren't leaks. Seal any open pores in the PLA plastic, as it can act like a sponge under pressure. Once it's dry, repeat the test. This time it should stay completely watertight. To cut the acrylic pipe to size, let's 3D print this custom pipe cutter holder I designed specifically for this tube diameter. The STL file is included with the project files. Insert 2 M3 hex nuts, thread in a pair of bolts, and the tool is ready to use. The submarine's pipe length needs to be exactly 288 millimeters, so mark that point on the tube, clamp the tool in place, and cut flush with a hacksaw. This method keeps the cut straight and clean. Afterward, use a deburring tool or hobby knife to remove any burrs. Just be careful, as the edges can be sharp enough to cut skin. With the pipe cut to length, slide it over the submarine until it meets the rear O-ring and seats snugly. Now let's waterproof the adjustable exo ballast weights. Separate each 1/4 ounce weight, peel off the sticky backing, and cover each one with a piece of heat shrink tubing. This not only protects the metal from water, but also keeps them looking neat and prevents rust buildup over time. For a cleaner finish, seal the ends of the exo ballast weights with a dab of superglue. Make a handful of these so you have extras for fine-tuning buoyancy. The exo ballast holder attaches to the submarine using the knobs and stays secure once both end caps are sealed. Now let's make the floating buoy that holds the antenna at the surface. Hot wire cut a circle from a thick sheet of polystyrene, mark the center, and mount it on a swiveling stick to chamfer the bottom edge. This step is optional. Cut a slot down to the center hole so the antenna cable can snap into place. Heat shrink any exposed metal for corrosion protection, then let the antenna rest neatly in its channel. The buoy is done and will simply follow the submarine across the water. Before we test the sub, let's set up its wireless charger using the custom casing I designed and printed. Insert a small magnet to make clip-on docking easy. Prepare the female DC jack by soldering on its wires and pushing it into place. Desolder the coil from the transmitter board, slot the board into its cavity, and wire the DC jack to its input pads. Resolder the coil using shortened wires, glue it into position. A tip here is to use the acrylic pipe as a guide for perfect alignment, and then fill the electronics cavity with hot glue for durability. Use a toothpick and marker to highlight the debossed text and icons on the charger for a nice finishing touch. For power, use a 12-volt DC adapter and plug it in. Now you have a fully isolated clip-on charger, so you will never need to open the sub to charge it. The only trade-off is that it takes around 8 hours to fully charge. If you want faster turnaround, simply charge it via USB-C with the front cap removed. For the quickest option, use a dedicated LiPo charger with a JST connector to charge directly, cutting the time down to about 1.5 hours. With the stand printed, the ESP-DIVE has a proper place to park, even with the exo ballast weights installed. It's perfect for display, or just keeping the sub off your workbench when not in use. Now for the exciting part, the first water test. We'll power the sub on with a magnet, load up the web server control panel, and gently place it in the water. The controls work and it drives nicely, but it doesn't submerge yet. That's expected. To prime the ballast, use a syringe to pump water into the front hose until it fills the tank and starts working as intended. During this first test, a bit of water managed to sneak into the hull, which is why testing is so important. To fix this, we'll disassemble the sub, loosen the O-rings, and superglue seal every 3D printed surface with open pores that could allow leaks. Even the coupling cavities on the inside. For extra safety, dry out the tail chamber thoroughly and coat every crevice with superglue. Once it's dry, reassemble and add a small couple of dabs of glue where the rear piece joins to keep it from popping off. I also noticed condensation forming in the front bubble, which means our first cap seal wasn't enough. This time we'll dry it completely and coat all of the PLA with superglue, even the outside. Some condensation is normal in colder water because of the air moisture trapped inside, but adding a few silica gel packets inside the hull should help absorb it and keep things clear. If water flow through the front hose seems slow, widen the bend with a short section of pen tube. This prevents kinking and improves suction. Lastly, I noticed the sub leaning slightly to one side and sitting a bit tail heavy. To fix this, we'll add 3 internal weights to the front right, 2 on the other battery, and a couple of weights on the rear piston ballast motor. This rebalances the submarine and keeps it level in the water. Let's reattach the external weight rack. I used 4 weights for fresh water and 5 or 6 for seawater, since everything is more buoyant in salt water. My sub was still a little tail heavy, so I removed 2 internal weights from the rear and moved them to the external rack in this configuration. It balanced out perfectly for me. As a final touch, we can color in the debossed text using a marker and toothpick, then protect the lettering with a thin layer of superglue. And with that, the ESP-DIVE is officially complete, weighing in at 608 grams. Time to power it up, connect to its Wi-Fi network, and load the control panel in your browser. Your video recordings will be saved to the microSD card in AVI format, organized neatly in folders for easy playback or transfer to your computer. For controls, the left slider runs the propeller forward and reverse, while the right slider steers the rudder. For the best experience, tilt your device horizontally to go full screen. This gives you access to both the camera feed and the ballast controls at the same time. Set both piston sliders to 90 for neutral buoyancy, move them to 0 to dive, and up to 180 to surface. If you'd rather follow a written guide, I've put together a full project blog on Electra Labs with diagrams, photos, and step-by-step instructions for building the ESP-DIVE. You'll find the link in the description. It's finally time for the ESP-DIVE's maiden test dive. Let's lower it into the pool and watch as the last air bubbles escape from the tail cone. With a quick tap on the control panel, we'll command the ballast tanks to fill, and there it goes, sinking gracefully beneath the surface. Now let's bring it back up. Listen closely. You can actually hear the piston ballasts pumping water out as it slowly but surely rises back to the surface. Driving it around really feels like piloting a true unmanned submarine, not just another underwater drone. So after a brief test of taking it underwater, submersing it, driving it back and forth a little bit, I brought it back up, and so far so good. There has been not a drop of water that's entered the submarine, so let's keep going. The ESP-DIVE's turn radius is a bit wider than a typical underwater drone, so it really shines in larger pools or open water. Speaking of which, let's take it somewhere bigger. Here we are at this natural pool I found near my local river. With speeds of about half a meter per second, it's quick enough to explore the entire area without feeling sluggish. If you spot a little condensation in the submarine, that's just moisture inside the hull reacting to the cold river temperature. Alright, it's time to test the sub out by some coral reefs. See you out there. This is the submarine's first time in the ocean, getting to dive around some stunning Caribbean marine life. I'll be piloting it from my kayak, staying within the 50-meter range of the antenna buoy. With the ballast set to neutral buoyancy, it's amazing to stop at one depth and hover in place, almost like a tiny research sub. Thanks to the 5-meter cable length, we can really get down there, close to the reef, around the fish. And what you're seeing now is the live footage straight from the ESP-DIVE's onboard camera. Imagine exploring spots like this in your own local lake, river, or reef with something you built yourself. After about 30 minutes of runtime, the battery is running low. Time to surface and bring her home. Now you've seen what the ESP-DIVE can do. If you want to build this submarine, you might want to save this video to your watch later so you can follow along whenever you're ready. All the files, code, and parts list are linked in the description below for you to get started. Before you dive in, pun intended, remember, waterproofing takes patience and relentless testing. Seal every vulnerable connection, even if it means drowning it in super glue. I go through like 12 of these per week. Water is brutally unforgiving of mistakes. And if you loved this project but want something easier, I've made a full ESP32 project playlist with all sorts of fun projects on a simpler level that I'm sure you'll enjoy. Your next project is waiting. Tap the playlist now. Remember, if you can imagine it, you can make it. And I'll see you in the next build.